All right, so graphs and number lines set builder and interval notation. So what I want to do is I'm going to consider the graph of the number line here, and I want to show you how we represent this interval where 2 is included in this set all the way up to 5, except 5 is excluded. So numbers that are in this set, just kind of basic numbers. I know that x equals 2 is in the set because it's closed on that set. Now all numbers bigger than 2 are also in that set, so I can say x is equal to like 2.01 or even bigger, 2.1 and so on, all the way up to say x is equal to say 4.99 or even 4.99999. But as soon as you get to 5, then you know it's excluded out of that set. Now numbers like 2.9 and 3.1, so pi is in here, 3.14, 3.9 and so on. So all numbers between 2 and 5, including 2 but excluding 5. And how do we write this, you know, in set builder notation, then also in interval notation? So set builder notation, it looks like an inequality. So it says it's a set x such that x. Now what they're going to do is they're going to define, you know, what x values are in. And so we know that it's going to be 2. X is going to be between these numbers all the way to 5, and then we're going to close this. So I need to put inequalities here that you know correspond to the numbers that live in this interval. So I know that numbers that have to be bigger than 2 and then also have to be less than 5. So this means x has to be bigger than 2. So if you look at that this way, you can see that x is the bigger number, 2 is the smaller number because you know it points at the smaller number, or the alligator eats the bigger number. And we also have to say that 5 is going to be less than x. So if I look at this, just 5 and x, we know that 5 has to be less than, well, x has to be less than 5. So, you know, 5 being the bigger number, x being the smaller number. Now, remember that 2 is included, so in order to include it, we put an equal sign here. So you can see that, you know, 2 is less than or equal to x, then x is less than 5. So these are the numbers between 2 and 5 where 2 is included. Now let's call that example A. So example B, let's do a similar number line. Let's say 0, 1, 2, 3, 4, 5, 6, 7, 8 again. I'm not labeling them all again. I'll label the numbers when we put them in here. So let's say we're going to go from 3 to I don't know, 6. Let's go from 3 to 6. Now what I want to do is I want to exclude the 3, and I'm going to include the 6. Then all numbers in between these things. So the way we do this in set builder notation is we say this is going to be all x such that we know 3 is going to be, you know, x is going to be between 3 and 6, and then we just have to know what we include. So, you know, x is going to be the bigger number, and again, 6 is going to be the bigger number. So it's nice when you see these, say, two-sided inequalities, the arrows will always point this way. Now 6 is included, so we have this. Now in order to write these things into interval notation, we'll do them over here. So if I want to write this exact same set in interval notation, so this would be set builder, this will be interval. So it's going to go from 2 to 5. So we're going to go from 2 to 5. Now we include the 2, so we put a bracket around it, but the 5 is not included, so we put a parenthesis around it. So very similar here, our interval is going to go from 3 to 6, so it's going to go from 3 to 6. You know, 3 being excluded, so it's going to have the parentheses, 6 being included, so it's going to have the bracket. So we'll also do ones that, you know, that go off into infinity or say negative infinity. So maybe another set over here. So for C, let's give us the number line, I don't know, let's go all the way to 7, for instance. And I'm going to go from negative infinity to 7. So all these numbers in here. Now let's exclude the 7. We'll include the next one next time. So numbers that would be in here is like, you know, 6 is in here, 5 is in here, 4 is in here. Also all the numbers between them. So all the way to 0, negative 1, negative 2, all the way to negative infinity. So there's there's an infinite amount of numbers in this set, just like all these sets, except this is going to be unbounded to the left. Now the way we're going to write this in set builder notation is we're going to write x such that, now 7 being our important number, this is where we're going to stop at. So since it's the only number that really defines this set, the only real number that defines a set, we do x and then we do 7, and then we ask ourselves, what way is it shaded? Notice that there's not two spots where this thing ends. It doesn't end. This thing goes all the way to negative infinity. So we don't really write negative infinity in the set builder notations. We just say one way or on the other of 7. So it's really nice is when you just have a variable and its number, the inequality is going to point in the direction that you shade. And you can see that you shade left. So this is actually going to point left. And another way you can see that is like all x values less than 7. Like 6 is less than 7, 5 is less than 7, 4 is less than 7. Even if you care about like all the numbers between like 4.2 is less than 7, 4.9 is less than 7. So you can see that all the numbers in this set actually satisfy this inequality right here. Now if I want to write this in interval notation, we actually do write this infinity in there. So we know that it's going to go from negative infinity all the way to 7. Now 7 is excluded, and infinity is not a number. It's actually a theoretical, well in this case lower bound. So you can't really touch infinity because no matter what number you pick, you can always pick one smaller. So we always leave the infinities as excluded. Now, let's do another one. Let's go the other way. So what if I want to go from, let's say 1, and let's include 1 all the way to positive infinity. What if we want to go the other direction? So again, this is going to include numbers like, it'll exclude 0 because it's to that way, but 2 and 3 and 4 and 5 and 6. So, all these numbers are going to be included. Even the numbers between like pi will be included as well. So all the numbers 1 or bigger. So the way we write this is x such that we know we're going to have x and we're going to have the number 1. Since this is really only stops at one real number and then is unbounded, x is going to be, well, remember that if you only have one variable with the number, it's always going to point in the direction that it's shaded, and it shades to the right, so this is going to point to the right. Or you can also think about the numbers that are greater than 1. So like these numbers in here satisfy this inequality. So 2 is bigger than 1, 3 is bigger than 1, pi is bigger than 1. So all the numbers in this green set will satisfy this inequality here. If I want to write this in interval notation, we actually do include that. This thing goes all the way to the right forever and ever and ever. So this is going to go from 1 to infinity. So it's going to go from 1 to infinity. In this case, this is filled in, so it's going to include the 1. So we do a bracket, and we never touch infinity. It's not a number. It's a concept. So what I want to do is I want to bounce between, all three of these. We went from number line to this. Basically, I want to be able to go from here to here, or maybe even from here to here. Just kind of get familiar with just interchanging these ideas. So we'll go from set builder and then write the other two, and I think that should do it for us. All right, so let's say, example would be given the set builder notation. Draw the graph of the number line. And an interval notation. Okay. So the first one is going to be a. Let's say all x such that such that 5 is less than or equal to x, which is less than 7. So if I want to write this, this is what we're given, the interval notation. I want to do a graph of the number line and then eventually interval notation. So our number line, we know we're going to go from 5 to 7. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Really just trying to get numbers less than this and bigger than this. But really, sometimes you can just go 5 to 7 and then just draw it accordingly. You don't have to be so refined. So we are going to start at 5, and since it equals it, this little equals bar means it's going to be filled in. This one doesn't have an equals bar, so it's going to be an open circle, so we're going to be all numbers between. So you could have just just did the 5 and the 7 and did it that way. That would be just fine. Now if I want to write this as interval notation, let's do it over here. Let me erase this since it's equivalent. If I want to do this in interval notation, the two numbers that are important are going to be 5 and 7. So this goes from 5 all the way to 7. 5 being included, so we have a bracket. 7 being included, so we have a parenthesis. Let's do an unbounded set. Say x such that, say x is greater than or equal to 2. So for an unbounded set, I know that 2 is going to be our only number. So we have 2, say here, 1, 2, 3, 4 here. Say 2 there. So 1, 2, 3, 4. Again, I don't need all these numbers. I could just do a number line with the number 2 and be happy with that. So I know that this points to the right. X on the left points to the right. Also, you can think about numbers bigger than 2. 3 is bigger than 2. 4 is bigger than 2. Really have to satisfy this inequality. It could also be equal to 2. So this is going to be filled in at 2 and then to this direction. So similarly, if you want to not write all those numbers, that's an equivalent set. If I want to write this in interval notation, we need to know where it stops and where it technically stops, though it doesn't stop, it's unbounded. So we know that we're going to go from 2 all the way to infinity, so 2 being included, infinity being a concept, theoretical upper bound will not include. So we never include the infinities, we leave them as parentheses. Now, let's solve a couple simple linear inequalities. And when you solve inequalities, what you get is you get a set as opposed to solving equalities. So let's erase this and solve some inequalities. And I'll show you kind of the difference between solving an equality and solving an inequality. Not much, frankly, not much at all. They're very similar. If you can do one, I guarantee you can do the other. So if I asked you to so if we have an equality, let's say solve x plus 5 equals 7. And then we have what's called an inequality, something very similar. Let's say solve x plus 5 is less than 7. Now inequalities will have less than, greater than, less than or equal, greater than or equal to. That's the only difference between an inequality having these signs as opposed to an equality having an equal sign. So we know that in order to solve this, we subtract 5 on both sides. So x is going to be equal to 2. Similar here, we're going to subtract 5 on both sides. So in this case, x is going to be less than 2. Now if I want to draw this as on a number line, 2 being the only important number, and similar here, I'm drawing this on a number line, 2 being the only important number. But being equal to means you just have a dot here. It's just 2. X equals 2, that's the only solution, as opposed to an inequality which has an infinite amount of solutions. That's a set of solutions that is larger than the singularity. So we have our singleton. So we have numbers that are going to be to the left of 2 or less than 2, so it doesn't include 2, unless that an equal sign, and it's going to go this way. Now, say if it does have an equal sign, what if it said equal instead? Well, the only difference is equal means it's going to include that 2. And we have equivalent notations. I can write this negative infinity to 2, close parentheses, or I can say x such that x is less than or equal to 2. So there's your number line, your interval notation, and your set builder notation. Notice that set builder notation is nothing more really than the original solution that we had, except it says x such that x is that. So if I want to solve some other inequalities, we know that they're very similar to solving inequalities. We just have equivalent solutions over here as far as how we write those sets. So what if I say, we say say 3x plus 4 is greater than 16. So just like an equality, what we have to do is solve this, the linear equation. We have to subtract 4 first and then divide by 3 next. So we're going to have 3x greater than subtracting by 4 is going to be 12. And then finally dividing by 3, x is going to be greater than 4. Let's divide by 3. Now I like to draw the number line first. So I have 4 here. We know that this is going to be numbers bigger than 4. X is greater than 4, but not including 4, so it's going to look like this. So another way we can write that is open the parentheses 4 to infinity if I want to write that as a interval notation, and if I want to write that as set mode notation, x such that x is greater than 4. Now our big difference between solving an inequality and an equality is what happens if there's a negative sign on, we have to multiply or divide by a negative. And tell you what, I'm gonna do this both ways so you can see why this actually works. We have to make sure that everything stays consistent. So if I have let's say I have an example I already prepped for this. Minus 2x, let's call this C. Minus 2x minus 1 is equal to less than or equal to 5. So if I want to solve this, I'm going to make sure that you can see all these things, but so minus 2x minus 1 is less than or equal to 5. So the way we're going to solve this is we have to, add 1 first. So minus 2x is less than or equal to 6. And then finally dividing by negative 2. Except when you divide by a negative number, what's going to happen is it's going to change the sense of the sign, so it's going to change its direction. So when you divide both sides by that negative 2, instead of it being this way, it has to flip. Change the sense of the sign is what we say. So then that means x is going to be greater than or equal to 3. So if I draw that number line, this is 3, and then 3 to be bigger than it or equal. So this way. So, interval notation, 3 to infinity. And set mode notation is nothing more than x such that this is. Okay. So I want to show you why. Unfortunately, I didn't prep this particular one, so bear with me as I make it work out nicely. So let's say I want to solve, say 5x plus 4 is less than, say, 3x. Make sure that this is going to be even. So subtracting 4, I'll say minus 12. Yeah, that ought to do. Okay. And I'm gonna basically do exactly the same equation over here. So 5x plus 4 is less than 3x minus 12. And what I want to do is I want to send them on both sides. I'm going to put all the x's on the left on this side and then put all the numbers on the right. And then for this one, I'm going to put all the numbers on the left and all the x's on the right. And I'm going to show you that, it's our choice on where we want to put x. And I want to make sure that things work out equivalently. So putting all your variables on the left, so I'm going to have to send 3x to the other side. So adding, subtracting 3x from both sides, what we get is 2x plus 4 is less than negative 12. And then subtracting 4, 2x is less than negative 16. Now, it doesn't matter that this is a negative number. The thing is when we do something to both sides, if I multiply or divide by a negative number, I'd have to change the sense of the sign. But this is a positive number. So when I divide both sides by positive 2, this sign stays the same. So this is negative 16, but divided by a positive 2, so that the sense of the sign gets to stay. If that was a negative 2, I'd have to switch it. So that means x is going to be less than negative 8. And you can see that here's negative 8, and to be less than it, it's going to be open circle, and then this way. Or we can say, minus infinity to negative 8, open. Now let's put all the variables on the right and all the numbers on all your constants on the left. So what I'm going to do is I'm going to subtract 5x on both sides first. So subtract 5x, subtract 5x. So then 4 is less than negative 2x minus 12. And then I'm going to add 12 to both sides. So adding 12 is going to be 16 is less than negative 2x. Now in order to solve for x, I have to divide by a negative 2. So when I divide by that negative 2, what you're going to have to do is change the direction of that sign. So this is going to be x. So then I have negative 8 is greater than x. And what you'll notice with these two sets here, our two solutions, that the arrow still points at the x and is still technically eating, the alligator is still eating the 8. Same thing here, we're still pointing at the x and the alligator is still eating the 8. That's why we have to change the sense of the signs to be able to make this solution consistent. So, this gives us the exact same solution. A lot of times I don't like your x's on the right of these things. The first thing I do is I rewrite it to where your x is this way, because if your variable is here and your constant's here, when you draw your number line, it's going to shade in the direction of that arrow. So if x is over here and your number is over here, it's going to shade, that way. So it's going to go open, boom, done. All right, last one, just got a word problem that can get confusing, so I wanted to do one, and that'll finish it. So similar to an example, you're probably going to see the homework. It says auto insurance will replace your car as long as the price to fix it exceeds 80% of its value. They're not going to fix it if it's not worth it, is kind of the idea. So let's kind of put that in words. So, and insurance company will replace the car if the claim exceeds 80% of the car's value. Now, equivalently, we can say that if it costs less than 80%, well, actually, exceeds means strictly greater than 80%. So it's not going to replace your car if it's less than or equal to 80%. So I can also say it will not replace car if the claim is less than or equal to 80% of the car's value. All right, so here's an example. Let's say I got in a car accident and the repair was $9,300. So assume my repair claim is $9,300, and they did not replace the car. Really, what can we say about the price of the car? What can I claim about the original price of the car? So, what was the value of the car? Now, I can't tell you the exact value of the car, but I can basically say the car is going to be at least more than this. So what we know is they did not replace the car. So $9,300 was not enough to replace the car. So they will not replace the car if the claim is less than or equal to 80% of the car's value. So what that really basically says is that $9,300 was less than or equal to 80%, of value of the car, right? Or if I want to put, this into an equation, I can say 9,300, symbolic notation is what I mean by that. 80% being 0.8 of being multiplied, so times the value of the car. Let's just say x is the value of the car. So I have to solve this for x. So in order to get rid of a multiplication of 0.8, I'm going to divide both sides 0.8 by 0.8. So 9,300 divided by 0.8 is going to be less than or equal to x. So we're almost out of room. What I get is 11,625. So 11,625 is less than or equal to x. Now, I do not like to write x's on the left. I prefer them to be on the right hand side. So I'm going to rewrite it over here, that x is greater than or equal to 11,625, so dollars. And I think in your homework it says x such that x, and they put a little box here, and they'll say, what one, there's like 4 different things, so it's going to be greater than or equal to, and then they want to know a dollar amount here. So then you just put this, 11,625. Or whatever your dollar amount's going to be when they ask it. And that's it.